Hi all. So today we are going to discuss about a new technique, that is a multi-criteria decision making technique, that is called as the gray integrated decision analytics. So why it is called as gray? Maybe the popular technique of gray relational analysis you might have heard about. So the gray means that if the information is completely known, we say white. If the information is completely unknown, we say it is black. So gray is something in between. And this why this technique is used, because it has the capability to have you can accommodate multiple number of responses, it can have multiple number of alternatives and multiple number of criteria for evaluation. So all the three limitations that the other multi-criteria decision making techniques are suffering, so that can be solved with this gray integrated decision analytics. And we will be using a combination of different the distance spaces and the pairwise comparison for making this gray integrated decision analytics. So we will directly go to the implementation of the gray integrated decision analytics. So this is the first paper on this GIDA or GIDA. So this the literature review and the comparison with other methods are being detailed here. So I will be directly going to the methodology. So this implementation is about a 7-step evaluation process. So which will be having, first is about the pairwise comparison about the attributes. So you have several criteria for evaluation. So you can compare factor A with B. Okay, so if it is the value is 5, usually we use a 5-point or 7-point Likert scale. If the value is 5, means that A is 5 times more important than the second, or B. And in the reverse way, you can write B is 5 times less important than A. So similarly, like in ASP, the only thing is the difference in the scale for evaluation. We use a 5 or 7-point Likert scale here, and we can have the evaluation. So this is the comparison table and all. I'm not going with, we directly go with the steps for evaluation. Then we can have the important part in the evaluation is you can take the average of the responses. Suppose Aij is indicating the importance of one criteria, ith criteria over the jth criteria, which is evaluated by the kth respondent. So this is indicated by Aijk. Then we can take the average of the evaluation. So that will be the sigma k equal to 1 to n Aijk divided by n. So just we can keep the average for now. We are not using it anywhere. So you can keep it now, and we can calculate 3 different values. So one is the critical value of importance. So what is the critical value of importance? So suppose you are measuring in a matrix the factor comparison, A, B, C, D, etc. are the factors, and you are plotting them in the row wise as well as in the column wise, and you are representing all the pairwise comparison over the matrix. Suppose that we can see that this is the way we are representing it. Okay, then we can say that the critical value of importance is the least value that A is having, like least value A when compared to the other random factor B. And similarly we can say the ideal value is the highest value when one factor is compared with the other factor. So two comparison you are making, and the ideal value, critical value, and there is another thing what is called as the most typical value, which is the most likely value. So you arrange this in the order, increasing order, and finally you can represent the middle value, that is what we call it as the median of that we will be taking. So that will be representing the most typical value. So 3 measures we are taking: ideal, critical, and most typical. Then we are calculating the Whitenized weights. So these are the weights we are obtaining from the analyst, and we are taking the Whitenized weights from that. So what is the Whitenized weights? So critical value we are taking 1 time, ideal value you are taking 1 time, and 4 times you are giving weights to the most typical value, that the median value. So the critical plus 4 times the typical plus the ideal divided by 6, that will be giving the weights of the criteria. So this is how we determine the weights of the criteria in the gray integrated decision analytics. Okay, so this is the weights we are determining. Again we have a number of criteria. So there are m attributes or m criteria we are considering. Then we can calculate the normalized weights. So you can add all the weights, that is Wj divided by sigma j equal to 1 to m Wj. So you add all the weights and divide each weight by that, you will be getting the normalized weight for this. Okay. Then we have to, the fourth step is about, now the weight part is over, the fourth step is about the event outcome and the objective of the problem we have to determine. So what is the event, what is an outcome, and what is the objective? So the event, maybe we can say it as a selection problem, right? You are going to select something, or you are going to have a choose problem, right? You are going to choose something from the set of alternative. So an event become event outcome pair. So you have to choose something with an alternative. So such pair, that the selection problem with alternative 1, selection problem with alternative 2, that we can represent it as we represent it as the situation. So a situation is, we can say that, the problem with an alternative. Okay. Now we are evaluating the ranking of the situation set. So how can you rank that? So we can say that we will be calculating so a particular objective will be there. So if for the particular objective, we can say that objective here are the criteria, we can say. Suppose that maybe you are selecting a mobile phone based on memory, delivery, and maybe we can say about color. So color is a criteria. So with respect to color, you can evaluate this situation. So what is the situation? Selection comma alternative 1, selection comma alternative 2. So the best one can be ranked 1, the next best can be ranked 2, etc., etc. So this way we will be following that. So suppose that we have the, we can see that the criteria sum we are getting. So this way, suppose there are n number of evaluation. Okay, so this, how we will be doing this? So suppose there are n number of evaluators which are evaluating the criteria. So this ith expert is evaluating maybe the factor. So we can see that situation 1, the selection problem with respect to the alternative, selection problem and the alternative with respect to objective 1. That may be the first criteria. So he is giving rank 1, and maybe the second analyst is giving rank 2 or 3, etc. So this sum of the ranks we can take it. So okay, suppose that the sum of the ranks are 24, 26, 26 and 29. So which one will be ranked 1 here? When you have more number of evaluators are there, so the lowest one will be ranked 1. Why? Because that will be the lowest one. The rank will be rank 1 is always better than rank 2. So the lowest sum rank will be given as rank 1, rank 2 and rank 3. Like that, if there are two values are same, you assign rank 2 for them. If rank 1, so this values are 24, 26, 26 and 29, suppose, then you can take 24 as rank 1, 26 and 26 for the second and third, you are giving same rank, that is rank 2, and the 29 you don't assign rank 3, now you have rank 4. Okay, so this is how we will be doing the evaluation. Now we are calculating the distances from the ideal referential alternative. So suppose, what is an ideal referential alternative? The alternative which is having rank 1 for all the criteria, or maybe all the objectives for the evaluation. So this criteria, so the alternative which is having rank 1, that is 1, 1, 1, 1. So suppose there are 6 criteria, so 6 ones will be there. So that is the ideal referential alternative. So you take the distances, so we say as the bullseye distances from the optimal effect vector, or the best alternative will be taking. So how can you calculate that? The weights multiplied by R1 minus R01 the whole square plus the weights, second weight, W2 multiplied by R12 minus R02. What is R02? Is the ideal referential alternative rank. That is always 1, right? So R01, R02, etc. are 1, 1, 1 values, and R1, R2, R3 are the actual rank of our alternative. So this is how we are measuring the distances from the optimal effect vector, and based on that we can rank the alternative. So we can see that if the alternative is close to the optimal effect vector, then the bullseye distances are small. So this R1 minus R0, the modulus of this value, if this is small, we can say that this is the best alternative. So you can arrange the alternative in the order, and finally we can take the alternative which is having the least value of modulus of R1 minus R0. So this is how we do the evaluation. We will do with the actual problem now. Okay. So here we can summarize the steps, right? Identify the factors. You are doing pairwise comparison. Critical importance you are calculating. Ideal importance you are calculating. The most typical value you are calculating. And then you calculate the normalized Whitenized weights. Then you separate the events, outcome and the objectives. And for each objective or based on each criteria, you evaluate the event outcome pair. Okay, so this we are doing, and finally we are ranking the situation state. We are calculating the distance from the ideal measure and the bullseye distances or the ideal distances we are calculating. We along with that we rank the alternative. Here we are taking a case problem for illustration. You can understand from this. It is about a resilient supplier selection problem. So what is resilience? It's the capability of suppliers to manage or mitigate risk, or you can say that to come up from that. So if something is happening, they should be recovering from that and being positioned in a better position than the competitors. So this is how we take up the evaluation, and we can see that there are different criteria for evaluation. So for the selection, we take these criteria. One is quality, cost, flexibility, risk management, risk awareness, safety and concern for environment. So these are the criteria we are taking for the evaluation, and you can see the first three criteria, that is quality, cost and flexibility, we consider as the primary performance criteria. So these are the very important criteria, and all other are added for the extra criteria for resilience. So this resilient supplier selection problem we are considering for the evaluation. The details are given for the problem, so I'm not going in detail with that. So I'm directly going to the evaluation process. So we have the step 1, what is about pairwise comparison you are doing in Likert scale. From 1 to 7 scale I'm using here, and we can see that the evaluation, how we are arranging them. Then we are taking the ideal, critical and most typical values. So the step 2. So suppose that this is the upper triangle matrix evaluation. So there are how many criteria are here? Quality, cost, flexibility, risk management, risk awareness, safety and concern for environment. So there are 7 criteria for evaluation, and the analyst can rate the one criteria over the other based on the 1 to 7 scale. So the upper triangular matrix will be evaluating, and the lower triangular you can construct accordingly. Suppose there are 5 or 6 analysts for the evaluation. So how you will be accumulating their scores? So how can you accommodate those scores? So first you take the average of the scores from the analyst. So don't think that you are taking the average, you will be losing the data. So for that only we are considering this critical, ideal and typical values of the averages. So why we are considering that? Because we can see that quality when compared with a different criteria, so the lowest value is the critical value. So you can see that in the row wise 1, 1.5, 2.8, the values in that the lowest value is 1, and which is the highest important, that is the value is 4.5. that quality when compared to concern for environment, it is very high important. So we can see that quality is having the highest or the ideal weights are 4.5, and typical is the median value. You arrange in the order of increasing order of this, and you will be getting the median value as 2.833. So this is how we'll be calculating, and how we are whitenizing that. The ideal plus critical plus 4 times most typical divided by 6, you will get the whitenized weights. Now this way you calculate the weights for all the criteria here, you can see that, and finally what you are doing, you take the sum of the weights and divide each of them by that, you get the normalized weights of the criteria. So here as we are not checking for any consistency, because we are taking the average and we are considering that the inconsistencies can occur. That's why we are taking with the ideal. We are not directly relying on the evaluation, we directly rely on the ideal, critical and typical measures, so that will be reflecting the proper way that the weights should be. So this is how the pairwise has been pairwise comparison based evaluation of weights has been performed in GIDA, which is different from any other technique. So we can see how we arrive at a normalized weight for the criteria. So next we are taking the normalized weights we have calculated, and we can see that the which one is having the highest weight, the quality is having the highest weight. Okay, Now we have to define the event, outcome and the objectives. That is what we are doing. So event of the problem, we can say that there are 6 different alternatives. So how many the situation sets we can consider? The problem that we can say it is about the SRS. So the event is SRS, that is supplier resilient supplier selection, or selection of resilient supplier, that we take it as SRS. So how many event outcome pairs we can make it? So it is about SRS supplier 1, SRS supplier 2, similarly to supplier 6. So that way 6 different situation sets we can create. And now how you are going to evaluate the situation sets? So the situation sets we will be evaluating based on the criteria. So each criteria you are taking as each objective for evaluation. So who is performing best in quality will be ranked 1, and who will be performing in other criteria, that cost will be ranked 2. Similar to that way we will be doing the evaluation. So for this comparison, ranking comparison also, how we can combine the opinion of the analysts, we can see that. Suppose there are the 6 analysts for evaluation, right? So we have different ones. So suppose for supplier 1, we can see that the for quality attribute, supplier 3 is the best, supplier 2 is second best. So similarly you have evaluated 1, 2, 3, 4, 5, 6. Similarly for cost you have evaluated, you can see supplier 5 is the best. So you do an evaluation or the ranks of the supplier based on different criteria. Okay, so this is what we call it as the objectives here. So based on objectives we are evaluating, and finally you are taking the sum of these ranks. You can say that quality for supplier 1 we got a sum of the rank as 30. Okay, then how can you do the further evaluation? We can say that in the sum value, sum of the ranks, we can take the lowest ranked one, that will be ranked 1. So again, from the consolidated sum rank matrix, we convert it into a consolidated ranking matrix. How we can do that? The rank sum matrix is converted to a consolidated rank matrix, that is the lowest value. Here it is 6, that is supplier 3 has been evaluated by most of the analysts as the best one. So we take it as rank 1, supplier 2 as rank 2. Similarly, we do the evaluation. Now we can calculate the bullseye distance. This is a consolidated. First one is the rank sum matrix, and second one is the consolidated rank matrix. So this is how we evaluate or consolidate the ranks here. Now we can calculate the bullseye distances. How we can do that? Here there are 6 different objectives are there. So 6 situation sets are there. So 6, 1, 1, 1, 1, 1, 1. So the ideal best alternative consists of rank 1 for all the criteria. So that is what R0 is representing, 1, 1, 1, 1, 1, 1. So this is indicating the best for all the criteria, and we are calculating this is the ideal referential service supply. So from that we are calculating the bullseye distances. So how we can calculate the bullseye distances? This is equal to R0 minus R1 square of that, right? So you are taking the square of that. Okay. Suppose for example we can say supplier 1 for quality. So what is the consolidated rank for supplier 1 quality? It is 5. So 5 minus R0. R0 is always 1 only. So 5 minus 1, it is 4. The square of that is 16 we are getting. Similarly, for all the other criteria, supplier 1 for quality, cost, etc., you are calculating the R minus R0 or R1, R2 minus R0. The square value we are taking. Okay. So the values are indicated as such here. Now we are taking the sum of the values. How the sum are being calculated? The weights multiplied by so what are the weights? The relative weights we are calculated, or the normalized weights multiplied by this square value. So 2.242 multiplied by 16 plus 0.209 multiplied by 16. That is the sum of these values for supplier 1. Okay, so the sum are calculated, and from the sum we are calculating the bullseye distances. Okay, so the root of that value, we are calculated the different squared value, and the square root of that will be getting the bullseye distances, and the lowest bullseye distance is assigned rank 1. So here which is the best supplier? 1.5, which is having the lowest value supplier for, that is the best supplier for this case. Similarly 1.9 is the second best, so that is the rank 2. So this is how we order it and get the rank.